Okay, so today we're going to switch gears. We're going to start with chapter 5. 5.1 is called the integral. Antiderivative. The integral. Okay. So first note. Hopefully I don't have to convince you about the importance of being able to find areas, how much space something takes up. Here's an interesting thing about areas to note though. So we do another example. Again, I'm going to sort of use the distance and velocity and position and all that stuff to illustrate a point that I'm going to want to make. Suppose we have a graph of time versus, say, velocity. And suppose I have constant velocity, right? So I'm just moving at a certain speed in one direction. Let's say 80 miles per hour. Time starts at 0 here, and let's say this is 3. And let's say I ask you to find the area between 1 and 2. Right? So the question is find this area. And then answer the question, what does it represent? So we had a similar graph before when we were talking about derivatives, where I gave you the graph of the position function and asked you to find the slope of it, and it turns out, hey, that gave us velocity. That kind of talk segue into rate of change. So now I'm going to give you velocity, and I'm going to ask you about the area under the velocity function, and ask you to interpret it. So what's the area here? What's the area of 1? It's a rectangle.
X times y.
It's 80, right? Length times width. That's the area of a rectangle. So this length here is 1 times 80, right? So you basically get 80 times 1. So the answer is 80. Now that number 80, what does that represent?
Distance. Velocity.
Acceleration.
Well, let's look at the units. Right here I have miles per hour, and here I have hours. So what's the result going to be? The hours are going to cancel. The result will be miles. So in other words, this is a distance. What distance do you think that is, specifically? If you were to get more specific, what distance does this represent? This 80 miles represent what in this case? Over what? Over 1 hour, not just 1 hour, but the hours between 1 and 2. Sure, it's constant velocity, so it'll be the same along any hour, but specifically it's the hour between 1 and 2. Over the time interval 1 to 2. Right? Notice another way to think about this would be the following. If I take the position function evaluated at 2, it tells me my position at 2. If I subtract that from the position function evaluated at 1, it gives me my position at 1. If I subtract the 2, it tells me the position, the distance I've traveled in between them. So in other words, the area under the velocity function between these two times is actually the difference between the position functions at those two times. Now that's a very interesting relationship that we're going to take advantage of, right? Because now we know the relationship between position and velocity, right? So the area under velocity on 1, 2 is actually equal to the position function valued at 2 minus position function valued at 1. Also recall that the velocity is actually the derivative of the position. So in other words, if I look at the area under a function, under the derivative of a function, it kind of gives me information about the original function, which is, well, I find that interesting.
You said derivative of the position?
Yes, in other words, the area under the derivative of a function gives information about the original function. Just as how I can look at the original function, I can look at its slope and I can tell you about its derivative. In another way, I can look at the area under its derivative and tell you about the original function, right? So it's kind of like it goes hand in hand. It goes two sides of the same coin. You can flip one and unflip it in some way. So that's where we're going to want to take advantage of this new terminology here. It's going to make things easier to talk about. We say that a function f is the antiderivative of f of x if I take the derivative of big F and it gives me little f. For example, I can call S of t is the antiderivative. I'm defining the word antiderivative of v of t. So saying that v is the derivative of s is the same as saying s is the antiderivative of v. And based on what we've just learned, the area under the derivative gives you information about the antiderivative. Right? That's something that we're going to be using later on. Okay. So there's a lot of reasons why areas can be important, not just for the normal geometric considerations and the farmer wanting to measure how much land he has, but this kind of relationship is pretty important. So areas are important, and this leads to what we call the area problem. Figuring how much space something takes up. In math, this is often equivalent to finding the area under some function. for example, if a farmer has a rectangular field, I could easily find the area of a rectangle, but in theory, if I wanted to, I could put this on the Cartesian plane and use my coordinates. Think of this as a function and think of the rectangle as the area under that function. Right? I can always do that at any given time. Right? Just by drawing a picture to represent the situation, figuring out how much space it takes up can be equated to figuring out the area under a function. So now, how do we find the area under a function? That's going to be the question that the area problem, that's the area problem basically. So I have this random function, it's not necessarily a shape that we know about, it's not necessarily a rectangle or a triangle or a trapezoid or something that we have a formula for. It's some random function. And I want to find the area under that function between 2 points on the x-axis, A, B. Right? The area equals what? Right? This is what we want to do by answering the area problem. And you're going to see that that has a lot of applications. Just like how simply finding the slope of a function had a lot of applications, finding the area under a function is also going to have a remarkable number of applications. But that's kind of sort of why we care, and you'll see more about why we care later on. So, remember when we wanted to figure out the slope of a function, what we did was we used what we know about finding the slope of a straight line, right? That's a recurring theme in math. You want to figure out something more complicated, you kind of use simpler cases that you already know how to deal with and kind of build up to them, right? So basically what we're going to do to figure out the area under some random function is to use the area of something that we already know about, right? Easiest one pretty much is the rectangle. That's kind of the guy that defines area for us, right? When we first started thinking about area, we started with rectangles, right? Length times width we defined to be area of some rectangle, right? And so what we want to do if we want to find the area of some other space, we basically dissect it into a bunch of rectangles. You count the number of rectangles, add up all the areas, right? That's kind of what we're going to do. So the idea is, given a random function, and I want to find the area between A and B, what I'm going to do is I'm going to dissect this guy. On each of these dissections, I'm going to make a rectangle. Right? And so now what I'm going to do, add up all these areas of the rectangle, and it should give me roughly the area under this curve. Now remember, the curve is wavy, right? The rectangles are straight, so we are going to be missing some stuff, right? So this is an approximation, right? The sum of the areas of the rectangles is an approximation of the actual area. Now, as you can imagine, the more rectangles I use, the better the approximation is going to be, right? If I start splitting this one rectangle into two, I can fill in more space, right? And if I keep splitting rectangles, the better things get, right? But in general, what we're going to do for a random curve, to figure out the area, cut it up into rectangles that are under the curve, or it might be over the curve, depending on how we want to set it up. The sum of these areas is called a Riemann sum. Hence will be the name of that phrase you'll see in your homework. That's where it came from, right? basically, you dissect this into a curve into rectangles. You approximate the area of the curve by adding the areas of the rectangles. You say you've approximated the area using a Riemann sum, named after the mathematician who really developed the idea. So that's going to be called a Riemann sum. We have many methods for finding Riemann sums. So we're going to talk about a few in this class. So one is using, we're going to talk about three basically that I'm going to need to know. One is using what's called the right-hand endpoints. Basically, what's going on here, you have a random curve. You want to figure out the area between A and B. So you're going to do the following with the right-hand endpoints. Basically, step one, what you're going to do is you're going to partition the interval AB into n equal what's called subintervals. So I'm going to cut this into n sections, all of equal length, right? Each of these guys here, the whole thing is called an interval, right? The interval AB. And each interval dissection is called a subinterval. Now, notice that the following, the length of each subinterval called, not a new thing, we call it delta x, right? So the distance from here to here, we call that delta x. Now here's why we call it the right-hand endpoints. Use the right endpoint of the interval. Determine the height of the rectangles. So basically what I'm going to do for each subinterval, look at the right side, and I'm going to use that, keep going up until I hit the function, and I'm going to say that's the height of this rectangle. Do that for this guy, the right side, move up, hit that function, that's the height of that rectangle. Here, right side, move up till I hit the function, that's the height of this rectangle. Right side, move up, hit the function, that's the height of this rectangle. Right side, move up, hit the function, that's the height of that rectangle. We're going to add all these areas. 5, note the following. Riemann sum with n subintervals and right-hand endpoints is denoted R sub n. Another thing. Huh?
With n.
R, please.
With n
Riemann
subintervals.
sum with n subintervals. And right-hand endpoint is called R little n. R sub n. Right? Just to make sure that we know how to find this delta x. So let's say I'm cutting this thing into n subintervals, and I want to know what's the length of each subinterval. What do you think the formula that will give that would be? What's the length of this? Yeah, how would I know? Give me a formula for it. Let's say I wanted to cut AB into 4 sections, 4 equal sections.
Will it be subinterval?
What is the length of the first one?
The subinterval minus
The distance between A and B divided by 4, exactly. What formula is that? That's when n is 4, right? So what is going to be, what will be the formula in this case? N equals 4. Then delta x would be? What's the distance between A and B? How do you find the distance between A and B? Yeah, B minus A. B minus A. And then you're going to divide by 4, right? But 4 is just a representation for n, it's a specific value. In general, delta x will be b minus a over n. And for our purposes, it will always be that, right? In general, you don't necessarily have to use equal subintervals, but here we will. What? The theory looks complicated. When I actually do a problem, you're going to see it's just, what? How is it? I really have to be introducing these because these are going to be phrases I'm going to want to say. I'm going to want to say, oh, use right-hand endpoints and find the Riemann sum and find delta x, and I need you to know what these things are. So I have to give you this whole thing. When we actually do it, you're going to be like, what? What's that? So before I describe the other ones, let me actually just do an example with right-hand endpoints. So basically what we're going to do here is we're going to do right-hand endpoints, left-hand endpoints, and midpoints. Which they're all sort of basically the same idea. It just depends on where you determine the height of the right hand. So here would be an example. Approximate the area under y equals x squared on 1, 2 using R4. E. Is this an overestimate or underestimate? That is, the value that I'm going to use for the Riemann sum, is it actually bigger than the actual area or smaller than the actual area? So a problem with Riemann subs in the test would look very similar to this.
You said they're
So it
going to
might-
be bonus.
Come again?
You said that they're going to be bonus for chapter 5.
For the
Bonus
third
term?
test, yeah.
Okay.
Okay. So basically R4 means 4 subintervals. That means I want you to use 4 rectangles, and I want you to use the right-hand endpoints. So let's see how you kind of do it on the test. You don't even have to know how to graph the function, really. It's so easy. I'll graph it afterwards just for illustrative purposes, but so here's what we're going to do. So we know that we have the interval 1 to 2, right? So the first thing I'm going to need to know, and I'm going to dissect that into 4 equal parts. Now, if I take here, that's going to be my delta x. I'm going to want to find what my delta x is. My delta x would be what?
B minus A over
B minus A over
4.
n, which is 4. In other words, that's going to be a quarter. Which means the distance from here to there is a quarter, so this guy is 1 1/4, which is 5 over 4.
Yeah.
Plus a quarter, I get 6 over 4. Plus a quarter, I get 7 over 4. Plus a quarter, I get 8 over 4, which is 2. Right? So I just take the interval from 1 to 2, cut it into 4 equal sections, which I was told to do. Right? So it's not something I'm going to have to figure out. I'm going to tell you, use this many sections. Right? To find the length of each section, it's just going to be b minus a over n, which is a quarter. And so using that information, you can figure out what each endpoint is. Right? Now, here's what's going to happen. So remember, when I'm looking at each interval, I'm using the right-hand endpoints, right? Which means that when I'm looking at an interval, the only guy I really care about is the guy on the right. Right? So if I look at the first interval, I don't care about the 1. I care about the 5 over 4, because that's the one I'm going to plug into the function. Right? Similarly, if I look here, I would care about this guy. If I look here, I'll care about this guy. If I look here, I'll care about this guy. So notice I'm going to pick the right number on all the intervals, right? Now what I'm going to do with that number is I'm going to use that to figure out the height. So how would I figure out the height, you think? Let me draw a picture so you can kind of see. I want you guys to try to figure this out. So this would be y equals x squared, right? I care about between 1 and 2. Cut this into 4 sections, right? So the right side goes up, it's the function. 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 And this gives me the height of the rectangle. So if I were to ask you, what's the height of the first rectangle, what would you tell me? I take 5 over 4 to get the height, I plug it into the function, and it gives me the height over here, right? The height is actually just f of 5 over 4, right? So if I take 6 over 4 to figure out the height there, I just take f of 6 over 4. Plug in here, figure out the height there, I get f of 7 over 4. At 2, plug in the height there, I get f of 2. So basically, I write this interval, dissect it into 4 equal parts, find the delta x, that allows me to find all these numbers, plug in all the numbers on the right into the function, and add them up. So the test points here will be x equals 5 over 4, 6 over 4, 7 over 4, 2. Which means the heights are going to be f of 5 over 4, f of 6 over 4, f of 7 over 4, f of 2. That's actually confusing. And here I know that my f of x is actually just x squared. So, if I'm looking at these rectangles, what are the widths of the rectangles? Well, it's delta x, right? Each of them is going to be delta x. That's going to be the width. Now the function values gives me the height. So how would I find the areas of all these rectangles? I'll take the width times the height for each of them, right? So the area of this one is going to be delta x times f of 5/4. Plus the area for this one is going to be delta x times f of 6/4. The area for this one is going to be delta x times f of 7/4. The area for the last one is going to be delta x times f of 2. Or I could write that as delta x times everything, the sum of f of 5/4 plus f of 6/4 plus f of 7/4 plus f of 2.
That's for what? For the length you said?
That's for the areas. I'm finding the areas here. I just take length times height, right?
Okay.
So it's width times height, width times height, width times height, width times height, and I add them all together. The width for everyone is delta x. It's a common term, I can factor it out. So I kind of have this formula, which I'll give you a general formula. And so now, if I wanted to find R4, R4 would simply be delta x times f of 5/4 plus f of 6/4 plus f of 7/4 plus f of 2. Now my delta x I know is 1/4. What's f of 5/4? Right, 5/4 squared plus 6/4 squared plus 7/4 squared plus 2 squared. Just plug into the functions. So I get 1/4 times 25/16 plus 36/16 plus 49/16 plus 4. And this here is an approximation of the area. B, do you think this is an overestimate or an underestimate? Overestimate. You can see from the picture here, my rectangles are actually bigger than the function. So the area of the function is actually going to be smaller than the area of the rectangles. The area of the rectangles gives me extra area here. So this is an overestimate. Because it's larger than the actual area.
So why do you score the values there? Why do you score the values?
Why did I use what?
Why did you square?
Because that was my function. Remember, the height is
Oh,
given
yeah,
by the
x
function,
squared.
so I'm just going to
Uh-huh,
plug into the
uh-huh.
function, which was x squared. And then based on the picture, I could see that this was an overestimate. Here's another Here's another kind of thing we want to use, and I'll illustrate with an example again. It's called the left-hand endpoints. Similar to right-hand endpoints, except you take the left-hand side of the engine. We can also talk about the midpoints. Method of midpoints. And by the way, the left-hand endpoints you'd call Ln. This is similar to above, except use the midpoint of each input. This guy we call Mn. Yes. Yeah. So there'll usually be something in the problem saying, oh, really your answer is the sum of fractions or something. You don't have to Let's give an example. That f of x equals x squared plus 1. Approximate the area under f of x using 4 subintervals and a right-hand endpoint on, so I have to tell you the area under f using, I have to tell you on the interval 1 to 5. Four subintervals and a right-hand endpoints. B left-hand endpoints. In other words, I could have said here, aka, I could have just said, find it using R4, or find it using L4, or find it using M4. You should, I could say this in several ways. You should know. So I'm just going to run through these problems like how you'd write them down on a test, and at the end I'll draw the picture, give you some illustrations so you can kind of see what's going on. By the way, in the test you'll only be asked for one. You're not going to be asked for seven. On the final. So this is the problem. You're given a function. You're told that you want to approximate the area under that function on subinterval, and it's going to tell you how many subintervals to use. and which method it wants you to use, right? So we already ran through the right hand, we'll do that again, then I'll show you the differences between the left hand and the midpoint, right? So here's how the first step. Which I highly recommend that you visualize the interval. So boom, you draw that, here's 1, here's 5, you want to cut it into 4 sections. Right? So you're going to need to figure out each of those. Right?
Using the formula.
So the second thing you're going to do is you're going to figure out delta x. Delta x is going to be b minus a over n, which in this case is going to be 5 minus 1 over 4, which is actually 1. So it means you're jumping by 1 every time. So 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 1 equals 4. Right? I keep adding 1. Plus delta x, plus delta x, plus delta x, plus delta x. So those are the numbers. Take the required test points. So that means here you're going to take, you want the right hand endpoints, that's what we're doing part A. So you take all the guys on the right side. 1 is ignored because it's on the left side of the interval. And so now the formula. Basically R4 is going to be delta x times f of 2 plus f of 3 plus f of 4 plus f of 5. Delta x was 1. F of 2 is going to be what? 5. Right, 2 squared plus 1. Plus this guy is going to be 3 squared plus 1. This guy is going to be 4 squared plus 1. This guy is going to be 5 squared plus 1. In other words, that's 5 plus 10 plus 17 plus 26. What's that? What's up? Huh? 58. That's the approximation for the area using right-hand inputs.
When using right-handed estimates, would it always be overestimated?
No.
No.
Depends on how the function looks, right? So if it's going like this, then the right hand will always be bigger than the left hand because the function is increasing. However, if the function is actually going like this, then the right part will always be smaller than the left part. The function is decreasing. So it depends on the function, right? It's not like it's right is always over or under. It depends on the curve that you're looking at. Right? So in this case, the right-hand endpoints would be an underestimate. In that case, it's an overestimate. So it depends on the function. You'll have to figure that out, you'll have to either find the exact area under the curve, which before long we will know how to do, or just draw the picture and see if it's obvious. Let's do B. Now we're going to do left-hand endpoints. So what we're going to do is, again, visualize the interval. 1, 5, and cut it into 4 sections. We're going to go to 2, find my delta x. B minus a over n, 5 minus 1 over 4, so that's just 1, so now I'm jumping by 1 each time. Now with the left-hand side, each interval I take the left number, the left number, the left number, the left number, the rightmost number is ignored. So that was the 3. Take points. And 4, I'm going to plug into that formula. L4 is just going to give me delta x times f of 1 plus f of 2 plus f of 3 which in this case is going to be 1 times 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. Right? That's going to be 2 plus 5 plus 10 plus 17. That's what, 34? That's the approximation of the error by the left hand. C, we're going to do midpoints. So now I'm going to visualize this is going to be halfway. So now I'm going to go here, 1 to 5. Cut into 4 equal sections. My delta x is going to be b minus a over n, which is 5 minus 1 over 4, which is 1. So this jumps by 2, 3, 4. Right? But now I don't take the guys on the left, and I don't take the guys on the right. I actually want the guys in the middle. That's called taking the midpoint. So what you can do is to find the first guy. So I'm pretty much going to average these numbers. The average of two numbers gives you the number exactly in the middle, right? So my first midpoint, x1 star, you should put a star, would be 1 plus 2 over 2, which is 1.5, right? Or 3 over 2. Now, once you figure out the first one, the distance between the midpoints is still going to be delta x, just as it was between the regular points. So here, if this is 3 over 2, and I add 1, which is 2 over 2, the next guy is going to be 5 over 2. Add 2 over 2, the next guy is going to be 7 over 2. Add 2 over 2, the next guy is going to be 9 over 2. And now the middle points are the ones that I'm going to plug into the function. That's what makes it a midpoint estimate. So this means that the midpoint with respect to 4 is going to be delta x times f of 3 over 2 plus f of 5 over 2 plus f of 7 over 2 plus f of 9 over 2. 1 times 0 over 2 squared plus 1 plus 5 over 2 squared plus 1 plus 7 over 2 squared plus 1 plus 9 over 2 squared plus 1. 1 plus 1 plus 1 plus 1, that's just 4, plus 9 over 4 plus 25 over 4 plus 49 over 4 plus 81 over 4. And I didn't answer that. What? Yes.
Why don't, since we're doing it the same area, the same part of the function, why don't we get the same answer?
That's a good question. Why didn't we get the same answer? Why are the answers different? Right? So here I didn't really show the illustration, so you probably didn't see it. So let's look at right hand left hand. So just by looking at those two, you'll see the difference. But remember, x squared plus 1 looks like x squared shifted up 1, right? So the part that I care about is kind of the positive part, so it's going to be like that. Where I'm going between 1 and 5. Right, so now here. Keep up between 1 and 5. That's my y-axis, my x-axis. My y-axis is x-axis 1. Now, when I cut this into 4 sections, and I take the right sides to create the rectangles, I will have this. So when I do that, it's actually going to give me an answer that's bigger than the actual area. However, if I cut this into 4 sections, and I take the left sides to create the rectangles, I have this. In other words, the area of the rectangles gives me something smaller than the actual area, right? So remember, these aren't the actual area, they're approximations of the area, right? So the right hand is going to give you something, in this case, not in all cases, the right hand is going to give you something that's bigger than the actual answer. The left hand will give you something that's smaller than the actual answer, right? The right hand gave us, I think it was 58. The left hand gave us, I think it was 34. Right. So the actual area is somewhere between 34 and 58. I'm not sure exactly what it is, but I know that these are the approximations with 4 intervals. And of course, the midpoint is going to be slightly different. Look at the midpoint. There's 1, there's 5, we're into 4 sections. But I don't use those sections, I use the middle. And then that creates the area of the rectangle. So you notice in the case of the right hand, the rectangles are always over. In the case of left hand, the rectangles are always under. In the case of the midpoint though, one side is over, one side is under, right? With this particular function.
It's looking at both.
What? So these are the intervals, 2, 3, 4. I don't take any of these points. I look at the middle. And then I shoot up a vertical line from the middle to hit that function. And that's where I cut off the horizontal line. Right, same thing, I go to the middle, shoot up, cut it off there, middle, shoot up, cut it off there. So they give us different answers because they're different approximations, right?
So you move to the left, you move to the right?
I go into the middle of every interval. That's called a midpoint. Right, so this one is clearly an overestimate, this one is clearly an underestimate. This one you're not so sure. It depends on how much this thing is over and how much that is under. They balance out, how much they balance out. So it's not going to be exactly clear with this one, but those two will be clear in this case. Right, so yeah, they're not going to all be the same answers because they're not all exactly the correct area. They're just estimations of it using rectangles. So in general, given an interval from A to B, let's say we cut it up into n sections. Then they usually label the A, called it x0, and the B, it's called xn. So that's x0, this is called x1, x2. Here will be xn minus 1, xn xn minus 2. And so based on that labeling, your Rn will always be delta x times f of x1 plus all the way up to f of xn. Whereas your Ln will always be delta x times f of x0 plus all the way up to f of xn minus 1. Your Mn will be delta x times f of x1 star plus all the way up to f of xn star, where this x star is x. The star just means the middle of the interval, right? So the guy in here, I'll call x1 star. The guy in here, I call x2 star, and so on and so forth. And these are general forms. So I can extend this for any n, any integer n. In all of them, though, your delta x is always going to be b minus a divided by n.
What is the
You're
star?
usually, what?
What is the star?
The star just means take the middle.
Oh.
It's a common notation to Alright, but basically you find the delta x by that guy, and then you're going to plug in numbers into the function, add them all together. The numbers you plug in depends on whether you want to do right, left, or middle. And it's going to be easier to figure out which. Just actually draw the number line, put in concrete numbers, and pick the ones that you need. So that's called approximating errors with Riemann sums. What else do I want to? Now the thing is, in theory, you're going to have to go to a higher math class to actually prove this and convince yourself of this, but I guess in the illustration you can kind of see. We can find the exact area by using an infinite number of rectangles. So the thing is, whenever I use a certain number of rectangles, there's always going to be some space missing. There's always going to be some error, right? And the idea is, the more rectangles I use, the more I fill in the gaps, and the more I don't overlap anything. And I kind of fill in all the little spaces, and it becomes nice. It becomes the exact area. So, but infinity isn't an actual number, so how do you think we're going to approach an infinite number of rectangles? Because infinity isn't actually a number. I can never really attain it, I can only kind of approach it. So, limits, exactly. Right? Whenever you can't attain something but you want to approach it, use limits. So basically, the actual area going to be equal. If I take any one of these guys but make n go to infinity, that will actually give me the actual area. So basically what I'm going to say is, for example, take the limit as n approaches infinity of Rn. So I'm going to say the limit as n approaches infinity of delta x times f of x1 plus all the way to f of xn. And my n is going to infinity, right? So I'm just I keep cutting up rectangles forever, right? And basically, if I take the limit, that's what I'm doing. I'm adding all these rectangles, I will get the exact area. Notation here is the following. Use this notation here. It's kind of a fancy elongated S, which stands for sum. Here. The right side we call the definite integral of f of x on AB. It gives the net area under F on the interval AB. So we take a Riemann sum, let it go to infinity, cut up in an infinite number of rectangles. That gives us the exact area. To represent that quantity, we use this expression, right? And it's called the definite integral of f of x on the interval AB, and it actually gives you the area under f. Here, A and B are called the limits of the integration. F of x is called the integrand. A is called the lower limit. B is called the upper limit. So what I want to say, A and B are called limits of integration, integrand, upper limit, lower limit. I don't want to define anything else. I'm going to want to talk about. No, not really. The process of computing this quantity is called integration. Integration is the process of finding the area under a function by taking an infinite Riemann sum. This is what you use to express it. For example, the actual area under y equals x squared plus 1 on the interval 1 to 5 is denoted this guy from 1 to 5 of x squared plus 1 dx. Right? Now if I say blah equals some number, what I'm saying is the area under this curve between this interval and that interval is that number.
What's the answer?
No, the answer is actually a number, right? But I didn't tell you how to find it yet. So far we know how to approximate it, we don't know how to find the exact number.
What we were doing though.
No, we were finding approximations.
Oh, okay.
Right? We were finding the area of rectangles, it wasn't the actual area of the thing.
Okay. So with this one, we getting a whole number or something like that?
Yeah, you'll actually get a number and it will be the exact area.
Okay.
If you actually do this thing, which in 205 you'll never actually have to compute that thing directly. If you were in 201, we'd actually have to do that. But
Good.
we're just going to actually jump straight to the shortcuts. Is there anything else I want to tell you? Wait, I do want to mention, what do we mean by net area? Basically, I kind of mean that we can have something like negative area. Basically, if your function is under the x-axis, the thing is when you plug in the x point values into the function, it gives you a negative answer, right? So technically, if you're under the x-axis, what you get is a negative area. Right? Whereas if you're above, call this E2, you get a positive area. So here it's going to be a positive area. If you plug this into the integral, it will actually give you a negative number. Right? So that's what I mean by net area. It kind of averages out the positive and negative areas. Right? So if you wanted the actual area, what you do is you take A1 and then you subtract the value that you get for A2. That's actually what's going on. We're never going to have to, the processes I'm going to give you, we'll never really have to worry about that anyway. Just for your education. This in my notes that we can sometimes use geometry to figure out integral from a to b of f of x dx. Example, what if I ask you, what is the integral from negative 1 to 1 of this function? 1 minus x squared x. So that's going to be, now we're not even going to learn a technique where we can actually do this, by the way, but it turns out we can do it in this case, because if I actually look at the function y equals 1 minus x squared, it's actually a semicircle. Right? You can write it as x squared plus y squared equals 1. So from minus 1 to 1, you're basically looking at the area under this function. So basically here, the area is going to be 1/2 pi times r squared. So basically pi over 2 is going to be 1/2. So I can do that without any computation at all. Which might tell me in the homework. I'm not actually going to ask you something like that on a test. That's too easy. Okay.
Easy?
Yes. But when you go home, you sleep on it, you wrap your head around the idea, you'll start to see it. We're introducing a lot of new concepts right now, and it's late. So your brain's like, what? Just think of this thing as meaning the area under this curve. If If you know that's a circle, you know the area of a circle, so you just use the formula. Same way, if I gave you something with a triangle, use half base times height. If the function looked like a rectangle, use length times width. You can figure out the area just using geometry. But of course, what if you don't know? What if your function is so weird you don't have a geometric formula for it? That's the one we care about. And that's going to kind of take us into the next section, 2. It's called the fundamental. Theorem of calculus. So if you didn't get it from the name, this is a super important theorem. It's not just the fundamental theorem of integration or the fundamental theorem of one little thing. No, it's the fundamental theorem of calculus, like all of calculus. Right? It's like the theorem, right? It comes in 2 parts. We're only going to sort of do one of them. Basically, it's a surprising theorem in the sense that it unifies the rate problem and the area problem. This is the theorem that connects figuring out how fast something is moving and figuring out the area under a curve. They're actually connected in some way with a formula. This is the theorem, which is why Newton and or Leibniz are known as the fathers of calculus. The truth is, we've been practicing calculus for thousands of years before either of them were born. But we're practicing the 2 parts separately. We thought of derivatives and integrals as completely different things, like they're not connected at all. Newton and Leibniz realized, hey, these guys are actually 2 sides of the same coin. Newton and Leibniz were the guys who realized, oh, if I take the area under velocity, I can actually tell about the position, right? They're the first people to actually notice that and actually come up with a theory that connects these 2. I can talk about the area under the derivative to tell you about the original function, right? And I can take the derivative of the original function to talk about the velocity, to talk about, the slope. And connecting those 2 was what no one has ever done before Newton and Leibniz. And that just that single idea just exploded with applications, right? And it's kind of why they're all known for it now. Right? So they take these 2 separate schools of thought, they connected it with one nice theorem, a very unifying theorem, and that created calculus as we know it today, which is a very beautiful and useful thing. Anyway, so part 1, or is it part 2? I think so. Part 1 of this theorem says following. Usually I prove this, but I already see eyes glazing over. I'm not going to do it now, I'll just tell you the theorem. Fundamental theorem of calculus, I'll probably abbreviate it FTC for short. So f is a continuous function, and f of x is an antiderivative of f, right? So for example, this guy could be a velocity function, and my big F would be the position function, right? That's just an example. So pretend I have a function, and I know what its antiderivative is. Then I can say the following. The integral from a to b of f of x dx, the area under the function f, is equal to big F evaluated at b minus big F evaluated at a. It's a very nice proof to get that, but I won't do it. This is a very important equation. This is part one of the fundamental theorem of calculus. It connects the area under the derivative of a function to the original function.
That's the one with the sine curve right here.
The what?
The sine curve that you showed us right here.
Sine curve.
With a neck.
This works in general. That's it. I'm going to do illustrations and all that soon. Okay, so one thing I want you to note. Antiderivatives are not unique. A single function can have many antiderivatives. In fact, every single function has an infinite number of antiderivatives. But I only need one, an antiderivative. I don't care which one I pick. It's not actually going to matter. If f of x is a function and f of x is antiderivative, then the most general antiderivative is big F of x plus a constant. Why? Because if I take the derivative of a constant, I get 0. So example, if I say f of x equals 2x, then all the following are antiderivatives. Right. For example, I can take big F of x equals x squared. I can have big F of x equals x squared plus 1. I can take big F of x equals x squared plus 17. I can take big F of x equals x squared literally plus any constant, right? These would be antiderivatives because if I take the derivative of these guys, I get that guy, right? And take the derivative of all of them, right? I can have an infinite number of antiderivatives. For this theorem, I don't care which one. I just pick one of them. And in general, I'm going to pick this one, the nicest one, where the constant is 0, so I don't have to write a lot. But that is important. We denote the general antiderivative by so f of x plus c, I write this down. This guy is called the indefinite integral. Notice it's indefinite because I did not give you any limits. I didn't specify what interval I'm on. So it's indefinite. I don't really know where it's going to work, but this is going to be the function that's going to make it happen. So that's called the indefinite integral. Or simply the antiderivative of f. They're kind of synonymous. Here's the essential idea. Let's just cut through all this theory. To find the antiderivative f of x, we need to find a function whose derivative is the original function. To do this, we can simply just reverse all our derivative rules. Right? So instead of going through the long way of Riemann sums and I can prove to you the formulas, we can just reverse the formulas that we already have. Now let's go back to basics, learn to walk again. Let's talk about the power rule. This time not for derivatives, but power rule for integrals. This rule says the following. If I take the antiderivative of x to the n, what should the answer be? Right? Now basically an antiderivative, I need to find the function. When I take the derivative, I get this guy. So then I think about what happens when I take the derivative. I multiply by the old power and I subtract 1 from it, right? Now you kind of want to reverse that process. So what I'm going to do is I'm going to add 1 back to that power, and then instead of multiplying, I'm going to divide by the new power, right? So that gives me x to the n plus 1 over n plus 1. And notice that this works if n is not equal to minus 1 because you divide by 0. This is a very important rule. It is called the power rule for integrals. Another rule that we know is the antiderivative or integral of e to the x. What's that going to be? E to the x, because if I take the antiderivative, if I take the derivative of e to the x, I get e to the x. So I will have that. I have this rule as well. The antiderivative or the integral of 1 over x dx is ln of x. Right? Because if I take the derivative of ln, I get 1 over x. So basically how you're going to think of these formulas is you're thinking of the derivative formulas backwards. Right? So the thing is, if I differentiate something that looks like this, I will get something that looks like that. If I differentiate this, I get that. If I differentiate this, I get that. Right? So you're kind of reversing a derivative, finding an antiderivative. So those are some basic rules. So let's do an example. What's the integral of 2x? Well, just blindly following this rule, what I'm going to do is I'm going to take x to the, this is a 1, right? So I'm going to take x to the 1 plus 1 over 1 plus 1. And then this 2 is going to stay there, which I'm going to talk about these properties later. That's going to be the rule. What's going to happen is this guy's going to become x squared over 2 times this 2. 2's will cancel, and you will get x squared plus c. Right? Now what you'll notice is that Well, if I take the derivative of x squared, I actually get 2x. Which is what should happen. Right? Or I can ask you, what is the integral of x squared? What's that going to be? X to the 3 over 3. I take x to the 2 plus 1 over 2 plus 1 plus c. That's x to the 3 over 3 plus c. Plus c is important if it's an indefinite integral. Right? Notice that if you differentiate this, you get that. What about the integral of x to the 7? You get x to the 8 over 8 plus c. Notice if I differentiate this, I get that. What about the integral of square root of x? Again, we rewrite this as x to the 1/2 because I want it to look like one of those rules. And so what I do is I add 1 to 1/2, which gives me 3 over 2. And I divide by 3 over 2. Plus c. Now notice that divided by a fraction is the same as multiplying by the reciprocal. So I can write this. This is just 2/3 x to the 3 over 2 plus c. And you will notice that if I differentiate this, I will get that. Just by reversing the power rule for derivatives, I get the power rule for integrals, which is in some sense the reverse of the derivative, not exactly because of this plus c thing. We could have a constant there. So these rules are important. These are just rules we know now. The fundamental theorem of calculus to find the following. Basically what you need to recall, the very important rule, that antiderivative from a to b, the definite integral, once I put numbers on this thing of the function, it is going to be its antiderivative evaluated at the top number minus the antiderivative evaluated at the bottom number. Any antiderivative, so I'm going to take the one without a c attached to it. So basically once I find, I'm given a function here, all I have to do is find its antiderivative and plug in the top number, minus the antiderivative and plug in the bottom number. So, for example, here I have 1 to 2 of x squared x. So I'm going to do, find the antiderivative, what's that? X to the 3 over 3. Now what I do is, the notation is the following. You write a vertical line, and you put 1 and 2. That's just notation. That's just reminding you that you need to plug in the 2, then plug in the 1. So what I'm going to do is I'm going to take the top number, plug into this function, minus, because the formula has a minus sign. I'm going to take the bottom number, plug into this function. So this is going to give me 8 over 3 minus 1 over 3 gives me 7 over 3. The other example, 1 to 5 of x squared plus 1 dx. What's the antiderivative of this? 3 using the power rule, it's going to be about 1. Plus x, right? Because the derivative of x is 1. Another way you can think of that is 1 is just x to the 0, add 1 to the power divided by the power of x. Right? Now I don't care about the plus c because I can take any one, I just care about plugging in these values. So I write this line here, right, a 1, a 5. And basically what that means is I'm going to take the top number, the 5, and I'm going to plug in here. Minus negative, open parentheses, it's going to be very important. I'm going to take the 1 and I'm going to plug it in there. Now I can kind of simplify. 5 cubed is what, 125 plus 5. This is minus 4 over 3. So I basically have 121 over 3 plus 5. 5 is what, 15 over 3? 15 plus this gives me what? 136 over 3? Is that right?
So why do you add x?
Because it's the sum. Right? So the x cubed over 3 is for this one, the x is for the plus 1.
So 1 becomes x?
The integral of 1 is x, yes.
Okay.
Because I have to figure out who do I differentiate to get 1. So let's end with a question. What do these numbers represent? What do you think this number means? What does that number mean? How do you interpret that number?
Actual area.
The actual area. Meaning, if I took the function y equals x squared, and I ask you, what is the area between 1 and 2? Not an approximation of the area, not a Riemann sum estimate, but what is the area? The area is 7 over 3. Crazy, right? Or if I say, okay, here's my function, x squared plus 1, and ask you, what is the area between 1 and 5? Not an approximation of the area, the actual area. Turns out the area is 136 over 3. So all those numbers that we were getting before, we actually did this one using Riemann sums. And I think we did that one using the right-hand endpoint Riemann sums. We got a bunch of different answers. They were all approximations of this number. That's the actual area under this curve. And we know that by the fundamental theorem of calculus. And
You have to use all that.
you have to use it if I actually use it. So if I ask you for an approximation, you would have to use the Riemann sums. But if I ask you for the exact area, this is how you would do it. And next time we'll do more of this and see some neat applications of it. And until then, I'll see you next week.